So we talked about linear regression. Polynomial regression is our next topic, and that's using higher order polynomials to fit your data. So sometimes your data might not really be appropriate for a straight line. That's where polynomial regression comes in. Let's dive in. All right, we talked about linear regression earlier, where we fit a straight line to a set of observations. Let's talk about polynomial regression, which is a more general case of regression. So why limit yourself to a straight line? Maybe your data doesn't actually have a linear relationship. Maybe there's some sort of a curve to it, right? That happens pretty frequently. Not all relationships are linear, but the linear regression is just one example of a whole class of regressions that we can do. So if you remember, the linear regression line that we ended up with was of the form y equals mx plus b, where we got back the values m and b from our linear regression analysis from ordinary least squares, or whatever method you choose. Now this is just a first order or a first degree polynomial, and the order or the degree is the power of x that you see. So that's the first order polynomial, but we could also use a second order polynomial, and that would look like y equals ax squared plus bx plus c. And if we were doing a regression using a second order polynomial, we would get back values for a, b, and c. Or we could do a third order polynomial that has ax cubed plus bx squared plus cx plus d. And the higher orders that you get, the more complex the curves you can represent, right? So, the more powers of x you have blended together, the more complicated shapes and relationships you can get. But more degrees isn't always better. Usually there's some natural relationship in your data that isn't really all that complicated. And if you find yourself throwing, very large degrees at fitting your data, you might be overfitting, okay? So if you have data that's kind of all over the place and has a lot of variance, you can go crazy and create this line that just like goes up and down to try to fit that data as closely as it can. But in fact, that doesn't represent the intrinsic relationship of that data. It doesn't do a good job of predicting new values. So always start by just visualizing your data and think about, how complicated does this curve really need to be? Now, you can use r squared to measure how good your fit is, but remember, that's just measuring how well this curve fits your training data, the data that you're using to actually make your predictions based off of. It doesn't measure your ability to predict accurately going forward. Later on, we'll talk about some techniques for preventing overfitting called train test, but for now, you're just going to have to eyeball it and make sure that you're not overfitting and throwing more degrees at a function than you need to. This will make more sense when we do an example. Fortunately, NumPy has a polyfit function that makes it super easy to play with this and experiment with different results. So let's go take a look. Time for fun with polynomial regression. I really do think it's fun, by the way. It's kind of cool seeing all that high school math actually coming into some practical application. Go ahead and open the Polynomial Regression IPython notebook, and let's have some fun. So let's create a new relationship between our page speeds and purchase amount fake data. And this time we're going to create a more complex relationship that's not linear. We're going to take the page speeds and make it some function of the division of page speeds for the purchase amount. And if we do a scatter plot, we end up with this. By the way, if you're wondering what this np.random.seed line does, that creates a random seed value. And it means that when I do subsequent random operations, they will be deterministic. So by doing that, I can make sure that every time I run this bit of code, I end up with the same exact results. Okay, and that's going to be important later on because I'm going to have you come back and actually try different fits to this data to see, compare the fits that you get. So it's important that you're starting with the same initial set of points. So there we have it. You can see that that's not really a linear relationship. We could try to fit a line to it, and it would be okay for a lot of the data, maybe down here, but not so much here. We really have more of an exponential curve. Now it turns out NumPy has a polyfit function that allows you to fit any degree polynomial you want to this data. So for example, we could say our x-axis is an array of the page speeds that we have, and our y-axis is an array of the purchase amounts that we have. We can then just call np, which is a shortcut for NumPy, polyfit x, y, and 4, meaning that we want a fourth degree polynomial fit to this data. So let's go ahead and run that. Runs pretty quickly. And we can then plot that. So we're going to create a little graph here that plots our scatter plot of original points versus our predicted points. And it looks like that. So at this point, looks like a reasonably good fit. What you want to ask yourself though is, am I overfitting? Does my curve look like it's actually going out of its way to accommodate outliers? And not really. I don't really see a whole lot of craziness going on. Like if I had a really high order polynomial, it might, swoop up here to catch that one and then swoop down here to catch that one and, get a little bit more stable through here where we have a lot of density, and maybe then it could potentially, go all over the place trying to fit this last set of data here. So maybe it would go woo, 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 for example. So if you see that sort of a nonsense, you have too many orders, too many degrees in your polynomial, and you should probably bring it back down, because although it fits the data that you observed, it's not going to be useful for predicting data you haven't seen. So imagine I have some curve that swoops way up here and then back down again to fit these data points. My prediction for something in between there isn't going to be accurate, right? It really should be in the middle here. So again, later in the course, we'll talk about principled means of detecting that overfitting, but for now, just eyeball it. Now we can measure the R-squared error. So by taking the y and the predicted values, we have an R2 score function in sklearn, scikit-learn.metrics that we can use that computes that for us. So basically it compares a set of observations to a set of predictions and computes R-squared for you with just one line of code. And our R-squared code for this turns out to be 0.829, which isn't too bad. Remember, 0 is bad, 1 is good. 0.82, pretty close to 1, not perfect. And intuitively that makes sense. You can see that our line is pretty good in this section of the data, but not so good out here and not so good up here. And 0.82 sounds about right. So I want you to get down and dirty with this stuff. Try different orders of polynomials. So go back up here to where we ran the polyfit function and try different values there besides 4. You could use 1 and that would go back to a linear regression, or you could try some really high amount like 8 and maybe you'd start to see overfitting. So see what effect that has. You're going to want to change that. For example, let's go to a third degree polynomial. Just keep hitting run to go through each step, and you can see the effect it has. So our third degree polynomial, definitely not as good of a fit. And if you actually measure the R-squared error, it's actually worse quantitatively. But if I go too high, I might start to see overfitting. So just have some fun with it, play around with different values, and get a sense of what different orders of polynomials do to your line, to your regression. And go get your hands dirty and try to learn something. So that's polynomial regression. Again, you need to make sure that you don't put more degrees at the problem than you need to. Use just the right amount to find what looks like an intuitive fit to your data. Too many can lead to overfitting, too few can lead to a poor fit. So you can use both your eyeballs for now and the R-squared metric to figure out what the right number of degrees are for your data. Let's move on.